So in this video, we'll take a look at actually two different concepts. One is the concept of power, and the other is the concept of efficiency, and they kind of go hand in hand. So the idea of power is it's related to the concept of energy, but rather than being the amount of energy that you use, it tells you something about how fast you use the energy. So there's a couple ways that it could be defined. Just in a simple way of thinking about power, power is the rate of energy use or the rate of energy production. So it doesn't matter whether you're using it or you're producing it. It's still telling you how fast the energy is going either in or out of the system. A little more technical definition, and the one we'll use in terms of making calculations, is that the work is the power per unit time. So that is to say that power, which is symbolized by capital P, is the work per unit time. So that would be work divided by time. Per means divide. This can lead to a little bit of confusion because there's a little bit of an issue with the labels on. Of course, work uses the symbol W, but then also this is going to be used as the symbol for the units for power, which is, of course, the units for work is joules. The units for time, the international standard, would be seconds. So therefore, that is joules per second, and a joule per second is called a watt, or called watts. And the symbol that's used for that is capital W. So these two W's do not mean the same thing. So this is the symbol for the property, work, and this is the symbol for the unit, watts. It can be a little bit confusing. But essentially, when you say that something has 100 watts, like for example a 100 watt light bulb, what you're saying is that that light bulb uses or produces 100 joules per second. Okay, so armed with that simple definition, we can take a look at some different ways in which you might apply the concept of power to practical problems. But before we can do that, it's really important to make a connection to the different forms of energy. And so if you can recall that energy is the ability to do work. So that means that any form of energy could be plugged into in place of the W here, because kinetic energy represents an ability to do work. Potential energy, elastic energy, light, sound, nuclear, all of these forms of energy all represent the ability to do work, and therefore the power equation is actually even a little bit more general. If you're asked for the definition of power, you definitely want to say work over time. But if you're asked for power in terms of, let's say, electrical energy or nuclear energy or any other form of energy, you can generically write it as P is equal to E over T. And then therefore, I could calculate the amount of energy in a system by saying power times time. So this is like sort of an alternate way of coming up with energy, not based on any of the energy equations, like for potential energy or for work or for kinetic energy, but instead I can calculate the energy. If I just know how much power is either being put into the system or how much power is going out of the system, then I can use those equations generically. So let's take a look at how this would look in a practical sense for an example problem, and we'll go through a couple of different examples so you can see how this would play out. So let's assume that Paula is pushing a heavy box using 120 Newton force over a distance of over 8 meters, and it takes her 15 seconds to make this move. And so if you are being asked to calculate the power, the formula for power in this case would be work over time. She is doing work because she exerted a force over some displacement. So important to remember, what is the formula for power? And the formula for power is F times D. We're not given any information about the angle, so we'll assume that the force was being applied parallel to the displacement, and then we need to divide by the time to come up with the actual power. So in this case, 120 times 8 meters gives me the work, and then when I divide that by 15 seconds, I'll come up with the power that was used in this particular example. So 120 times 8 equals, divided by 15 equals, so that turns out to be 64, and again the units are watts. Okay, so that's a simple example of how it would work. That's kind of straightforward, very low level, level 1, level 2 kind of problem. But let's take a look at how power can be calculated when you're not given the work, but you're given other information about energy that is being put into or out of the system. So we'll move on to a second example problem. And in this second example, we'll take a look at a car that accelerates from rest up to 15 meters per second, and it takes 6 seconds for this car to make this change. And so you're being asked to calculate the net power, and part of the reason why I'm being asked to calculate the net power is that we don't know anything about the losses. I mean, we know what ultimately ended up happening with the power that the car produced is that the car has kinetic energy. It is traveling at 15 meters per second, and therefore it has kinetic energy. But we don't know anything about the losses to friction. It's very likely that there is significant friction, and if there's not friction, then there's definitely drag. And those require the engine to produce more power than is actually getting produced or getting the finished product in terms of the kinetic energy. And so all we can really do with the information that we have right now, since I don't know anything about those frictional forces or drag forces or any of the resistive forces, is all I can really tell you is, in the end, how much power did we produce as a result of the kinetic energy that the car received. So again, power is equal to work over time, but in this case, we're talking about a change in kinetic energy, just like we learned in the work energy theorem. The work can be used to produce kinetic energy. And so therefore it's 1/2 mv squared divided by t. And now I can go ahead and plug in all these numbers. So 1/2, the mass was 1100 kilograms, times the speed of 15 meters per second squared, and all of that gets divided by 6.0. So we'll bring in the calculator. I'm going to put it over here. And that would be 0.5 times 1100 times 15 squared equals, divided by 6 seconds. So 20,625. And so we'll put that as the power is equal to 2.06 times 10 to the 4th watts, or 20,625 watts would be the same thing as 20.6 kilowatts. You're not required to put the answer in that form. You can certainly just leave it in the form that it was in. However, part of the reason I wanted to do that is because you will see this a lot. So for human beings to produce 1,000 watts of power is pretty difficult. You have to be in pretty good shape to be able to pull it off. But for a car or for heavy machinery to be able to pull off a kilowatt worth of energy, this is actually pretty easy for them to do that. So we will frequently be looking at powers that are fairly large, in the thousands of watts, in which case you really need to get familiar with this idea of kilowatts. This is going to come up again when we get to electrical power, where we will, generally speaking, think about electrical energy in terms of kilowatts rather than watts. So that was an example of the work was actually in the form of changing the kinetic energy. Let's take a look at a similar example, but instead of changing it into kinetic energy, we're going to change into potential energy. So let's assume that we have an elevator that has a total mass of 2,300 kilograms, the elevator itself plus its passengers, and it lifts the passengers up to the 5th floor, which is 25 meters above their initial starting position, and it takes 22 seconds. So in this case, we'll calculate the average amount of power. Again, we don't know anything about the losses or any inefficiencies of this, so all we can really do is just calculate the average power. So the formula for power is work over time, but in this case, the work is being transformed into potential energy, or that is to say, the work that is being done against gravity, and as a result, we're getting some potential energy, some storage of energy. And we can go ahead and start plugging the numbers in now. So 2,300 times, we're going to use 10 for gravity, and 25. And it took 22 seconds for this change to occur. And that's it. We can go straight to the calculator. 2,300 times 10 times 2,500 times 25, sorry, divided by 22, and we end up with 26,136. So we'll say 2.61 times 10 to the 4th watts, or 26.1 kilowatts. So there's lots of examples. Power, again, can be calculated using any form of energy: nuclear, thermal, electrical, solar. Any form of energy can be plugged into this equation. But the power equation really helps us to start thinking about a kind of related aspect that is not specifically related to power, but is very often framed in terms of the power being used by an object. And so we're going to kind of transition from making calculations of power, and obviously this formula can be used to do lots of things. You could calculate how high something went if you knew what the power was. If you knew the change in the kinetic energy, we could have calculated, I should say, if we had the power of the car, we could have calculated what would be the velocity of the car. So lots of variations of these problems that involve not solving for P, but actually knowing what the value of P is, and then using that to calculate other properties. But let's move on to efficiency. And let me give you a definition of efficiency, and then we'll take a look at how it plays out in practical problems. So probably the best definition of efficiency is it is the rate of useful work to the total work done. When I say rate, what I essentially mean is a ratio, meaning that we're going to divide the amount of useful work by the amount of total work that is done. So the amount of useful work that you get out of a system is always going to be less than what you put in. Unless you have 100% efficiency, you're always going to lose a little bit when you when in the real world. You're not going to get everything out that you put into it. We will probably use it a little bit more practical way of using it is to think of it as the ratio of the work out to the work that was put in. And what that's saying is that you're always going to put more work in than you end up getting out. In a very efficient system, you'll get most of the work out, but you'll still lose a little bit. It is framed in terms of work, but it would be just as valid for you to express it in terms of power. So I could say that it's the ratio of the power out to the power that was put in. And generally speaking, the efficiency essentially tells you how much is going to be lost to friction, drag, or other resistive forces. And those resistive forces typically result in producing heat. Can also produce other things like sound, but most of it goes into heat, and then that heat is just released to the surroundings and is now lost from the system. So if the system is a car or you're pushing a box across the floor, once that energy is turned into heat, that heat just dissipates into the surroundings and it's no longer part of the system anymore. And so it represents energy or power that was lost as a result of whatever action that you were doing. So the symbol we're going to use for efficiency is lowercase e, and it can be written as the useful work over the total work, or just as equally well, we could say the useful power divided by the total power. Okay, but in a more practical sense, I really won't usually write it like that, partially because it's just a little bit longer, a little bit wordier to write. What I'm going to say is that the efficiency is equal to the work out over the work in, or alternatively, it's equal to the power out over the power in. Okay, it can actually be expressed in two ways. So, really in a useful sense, it would be better to just simply use it as a ratio, because as a ratio, it's ready for you to use to do mathematical calculations with. Whereas with a percentage, you have to turn it back into a ratio in order to be able to do any math with it. So E can be expressed as a ratio, probably the more useful way of doing it, or a percent. So for example, I might say that the efficiency was 0.65, which is saying that for every 1 joule that I put in, I will get 0.65 joules out of the system. Or I could say 65%. Okay, so let's take a look at a problem, an actual real-world problem. We'll keep it very simple to begin with. We'll just do a couple really simple examples. and then we'll look at one more challenging one at the very end. So Harvey produces 450 joules of useful work by putting in 800 joules of work. Calculate Harvey's efficiency. So this is a very easy problem. So in this case, it's being expressed in terms of work. So it's going to be the work out over the work in. So that's 450 divided by 800. I'll express the answers in both ways. So 450 divided by 800 is 0.5625. So therefore, E is equal to, and I have two options. I can say 0.56, or I can say 56%. So very straightforward, simple calculation. You're just being directly told this is the lowest of low level problem for this. This is level 1. You're given everything. You just got to plug it in. It's just a simple plug and chug kind of problem. So let's take a look at one in which you were given the efficiency and you're being asked to find one of the other properties, so either the work in or the work out. So let's assume that we have a electric motor, and that motor is 80% efficient. Okay, if it produces 720 watts of useful, I should say, sorry, apologize for that, of useful power. So this is framed in terms of power, and I'm actually given the efficiency, and what I want to know is the power that was produced by the motor. So that is to say the input power, or the total amount of power that was produced by the engine, or by the motor. So E is equal to P out over P in, and what I'm looking for is this one. I want to know the power that was put into the system. So that means that the power in, I'm going to multiply by the power. That's going to move it over here, and I'm going to divide by the efficiency, and I'll end up with this. And then we can go ahead and plug in the numbers. So 720 divided by 0.80. 720 divided by 0.8 gives me 900. So the input power is equal to 900 watts. Now, since efficiency does not have any units, obviously, it's a power divided by a power, so whatever units that power has, those units would cancel. Same thing if I was doing work. So as a result, the units for this answer come from the power that was output. Whatever units that it was in, that's what the units of this will be. So this was in milliwatts, watts, kilowatts, whatever its units are, this one will produce the same units because the efficiency has no units by itself. Okay, let's take a look at one last problem, a little bit higher level, maybe a level 2 or 3 type problem, in which you're not just given the powers or the works, but you really need to calculate them by using one of the energy equations. So let's assume that you have an 1,860 kilogram truck and it accelerates from rest up to 21 meters per second by producing a total force of 4,900 newtons of thrust over a distance of 220 meters. And so what we want to calculate is the efficiency of the truck. So if you just look carefully at what's in there, on the top line, what I have is all the information that would allow me to figure out how much kinetic energy was gained by the truck. And on the second line, what I have is the total amount of work that was done by the truck. And what you're going to see when we plug these into the equation is that they're not equal to each other. And therefore, there is some inefficiency in the system. So there's some energy lost that did not end up going into the kinetic energy of the truck. So in this case, we're going to do this in terms of the work output over the work input. And you can see for this particular example that the work that came out in terms of kinetic energy, or some change in kinetic energy. And the work that was input was just simply work. So it was just force times displacement. So in this case, 1/2 mv squared divided by F times d. The force that a car exerts is based on the friction between the tires and the wheels, so that force is always going to be parallel to the direction of the displacement. So we can go ahead and put the numbers in. 1/2 the mass of the truck is 1860 times the change in kinetic energy, which is 21 squared. Obviously the initial velocity was 0, so we can just ignore that portion. And then on the bottom we end up with 4,900 times 220. And if this were 100% efficient, what I would find is that this efficiency would say that it was 1. So if I got all of the energy that was put in due to the work turned into kinetic energy, then this answer will come out to be 1. So there's the kinetic energy, and now I'm going to divide out individually each of the two numbers on the bottom. So divided by 4,900, divided by 220. And so what I end up with the answer is 0.38. So the efficiency is 0.38, or I can say 38% efficient. So that gives you some idea of how efficiency can be used. And again, it can be used with any type of energy, because work represents any kind of energy and power is based on any kind of energy. And so we can frame it in terms of work or energy, but ultimately it tells us something about what we're actually going to get out of the system. All systems have varying degrees of efficiency. Some are very efficient and might get 90 or 95%, and others are very inefficient. Cars, for example, are very inefficient. This is probably much better than the actual efficiency of the car. Typically, combustion cars are probably less than 20% efficient. So that gives you an idea of how to use power and how to use the concept of efficiency.